Hello and welcome to short video series for class 11. This is the first video for IIT aspirants, for NEET aspirants, for AP aspirants, for beginners, for freshers. This is the key concept, the oxidation number concept that we are going to dissect the concept till depth, which will be most essential for the beginners to have a foundation in chemistry. Now, you know there are many covalent molecules, there are many ionic compounds, and say for example we have carbon dioxide. These two are double bonds, and every bond is having two electrons, one contributed by each atom. So these are covalent bonds. Say for example water, covalent bond, ammonia, covalent bond. Let me draw the structure of sulfate ion. These are all covalent molecules and covalent ions which are bonded by mutual sharing process. Now the oxidation number concept has come from the covalent molecules, covalent ions. If these bond electron pairs are transferred temporarily to the more electronegative atom, and of course hypothetically, if they are transferred to the more electronegative atom, then what is the theoretical charge, the hypothetical charge that develops on each atom? That is called the oxidation number or oxidation state. Carbon will lose 4 electrons, so it will be having +4. The sign first, then the numerical, because it's not a true charge, it is a peak charge. So that peak charge, which is called popularly as oxidation number, is so very important in monitoring the progress of redox reactions. The utility of redox reaction and its prediction, balancing, mole concept all depends on your thorough knowledge on oxidation concept. Now each oxygen acquires a hypothetical charge of -2. So the oxidation number of carbon is +4 in carbon dioxide and -2 in each oxygen. Similarly, this is the sulfate ion, and this is a double bond, single bond. And if you look to each bond, and you will find that if there will be the transference of bond pairs to the more electronegative atom, hypothetically, on an imagination level, then sulfur will lose 6 electrons, 1 on this side, 2 on this side, 1 on this side, and 2 on this side. So the theoretical charge that will develop on sulfur is +6. So the oxidation number of sulfur is +3. Same concept can be applied to water. It is -2. This is -3. Because nitrogen and oxygen are more electronegative than hydrogen. So this concept is originated from covalent molecules and ions, but it is now used as a synonym of valency. Nobody now calls valency. Everybody says, what is the oxidation number? What is the oxidation state? And remember, oxidation state always pertains to a single atom. Now see, there are some rules, guiding rules to find out the oxidation number of an atom in a molecule or ion, which are very simple type. For actual oxidation number, you need to have a knowledge of the bond structure, the covalent bond structure, which is not as easy now. As a beginner, you will take 1 or 2 months more, if you are a fresher in class 11, you can't draw the bond structures of all the covalent molecules and ions. A simple rules you can remember that all atoms in their uncombined state, elementary state, will be have zero oxidation number. There is no compound, oxidation number is zero. Even if it is covalently bonded, for example, chlorine, the atoms are same. Oxygen, nitrogen, they're same. So if there will be a breaking of this bond, so the electron pair is not going to go to one atom. Each one will take back its own electron, and I'm showing a very interesting arrow. This is called fish hook arrow. One-sided arrow to represent one electron shift. So each atom gets back its own electron, so there will be no charge development. So oxidation number of each atom is zero if it forms a molecule but it is in the elementary state. Similarly, for oxygen in a compound, it is mostly -2. Majority of the oxygenated compounds, oxygen is -2, except in peroxides, O2 2-, where it is -1. There are two oxygen sharing -2 charge, so per one atom it is -1. This is superoxide, O2 single minus. So the share per one atom is -half. And this is OF2. Can you imagine? The one which was gaining electron will now lose electron to fluorine, because fluorine is more electronegative than oxygen. So it will be having +2. And in O2F2, it is +1. Because this is same, when the two atoms are same, there is equal distribution, no charge development. So the only charge that it will lose, electron it will lose on either side is one electron, so it will be having +1 charge. Same way, hydrogen in most of the compounds it is +1, except in metal hydrides it is -1. Now, in monoatomic ions like chloride, bromide, iodide, in a compound, oxide, nitride, phosphide, and in positive ion, sodium, calcium, or the variable oxidation state, ferrous, ferric, and all that, their oxidation number is equal to their charge, their valency. That is obvious, but that has to be a monoatomic radical or ion, right? Fluorine is so very highly electronegative. Electronegativity is the highest in the periodic table, so its oxidation number is always -1 in a compound. And oxidation number of a neutral molecule is 0 upon sum of oxidation number. For example, you take sulfuric acid. So if you are asked to find out what is the oxidation number of sulfur, then you take by X method. If hydrogen is +1 for 1, then for 2 it is +2 plus X for sulfur, and if -2 is for 1 oxygen, rule number 2, then there are 4 oxygen, the total is -8. So the sum will be equal to 0, so X will be equal to +6. So you can write down on the top of the atom it is +6. If it is an ion, supposing we are having dichromate ion, presume that both the chromium atoms are of identical structure. So we have to take it 2x. 2x minus 14, 1 oxygen is -2, so 7 minus 14 is equal to -2, not 0, because it is not a neutral molecule, it is an ion. So it's a polyatomic ion. The charge is equal to the sum of the oxidation number. So -2 is equal to the sum. So X comes +6. So you can write down in a pencil, because it's not the real charge. Or in a red pen or any other pen with a round mark so that it will be distinguished from the actual charge. Now let's go to very interesting examples. I urge upon you to watch till end. You will find great interest at the last scene. The climax will be very, very interesting. Now, if I ask you to find out oxidation number of simple molecules, say like perchloric acid, then if you are asked to find out for chlorine, then this is hydrogen is +1, chlorine supposing X, and oxygen -8 is 0. So X comes +7. So chlorine is here in the +7 state. So in the similar manner, supposing I'll ask you to find out what is the oxidation number of nitrogen in nitrate ion. So you'll say X -6 equal to -1. X is equal to +5. And so on. But the interesting case will arise when you have multiple atoms of a particular element in a compound or in an ion. You do not know at this stage what is the structure of the ion or molecule. So the only way for you is to follow the rules and find out. But here, supposing I'll ask you to find the oxidation number of both the nitrogen atoms separately. So since this nitrogen is in cation, positive ion, and this is in negative ion, so you can't do it by 2x method. You have to split them into positive ion and negative ion and find out separately. X +4 is equal to +1, so X is equal to -3. So this is -3 here. And for the nitrate ion, it is X -6 is equal to -1, so X is equal to +5. So this is in the +5 state. If you make it 2x, that you will get an average of +5 and -3. So you can't do that because the nitrogen atoms are in a different environment. It is in a positive ion, ammonium ion, where it is -3, and the other one is the nitrate ion is +5. Similarly, if I ask you to find out carbon by X method, you will fail unless you know that this nitrogen is -3. So you have to have a knowledge of the bond structure. So don't be scared. After some time, and in my short video series also, I will give you the tips of everything. So if this is the structure, nitrogen is more electronegative, then it will lose 3 electrons here. But carbon is little more electronegative than hydrogen. So it will gain 1 electron. So 1 electron will be gained and 3 electrons will be lost. So +3 - 1 will be equal to +2. So you can't apply X method unless you, from memory, you put nitrogen as -3. Similarly, this is called cyanamide ion. Supposing I ask you to find for carbon, then unless you know the structure of the cyanamide ion, you can't find. Of course, if you know from earlier knowledge that each of the nitrogen is -3, then you can do that. But here it will lose 2 electrons on this side of the double bond, 2 electrons from this side, so it will be +4. Similarly, OCN- is a very typical structure. This is a triple bond here, so the carbon, so it will lose 3 electrons from this side, 1 electron to this side, because both O and N are more electronegative than carbon. So in this Cyanide ion, this is cyanide ion, it is plus 4. But in cyanide ion or HCN, it is plus 2. Now these are very interesting things. Let's come about the most interesting paradoxical cases where by X method you will get something, but actually it is unacceptable. You get a fraction. So when you are getting a fraction or something, you are apprehending that a particular element is present multiple times, 2 times, 3 times. So it might be an average value. The actual oxidation number of each such atom of the same element might be different. I will take several examples to explain all these paradoxical cases. Now see, this is sodium pentasulfide. This, if you say that X method, you will say that it is plus 2 sodium plus 1 for 1, and for 2 it is plus 2 and plus 5x is equal to 0. So you get a fraction x is equal to minus 2 by 5. But actually if I draw the structure of the polysulfide ion, this is a long chain. These are sulfur-sulfur covalent bonds. So if you assign the oxidation number to each sulfur atom, then this will be 0. This will be 0. This will be 0 because the two atoms are same. So they will be broken in a homolytic manner, in a very even manner, so that nobody will gain, nobody will lose. This is called homolytic cleavage. And the other one where both the electrons will go to one side, that is called heterolytic cleavage. So here the homolysis will happen, of course, hypothetically, so that these three will have 0 oxidation state, and these two will have minus 1. Already they have minus 1, they have got some electron from some outside source. It's already minus 1, this is already minus 1. So minus 2 shared by 5 atoms. So the average is coming minus 2 by 5. But really, the internal sulfur, 3 internal sulfur atoms has oxidation number 0, and the terminal sulfur atoms have minus 1. Similarly, this is what we call the red lead. If you go by X method, you'll be getting plus 8 by 3, which is absolutely unacceptable, because lead cannot have plus 8 by 3 oxidation state. Actually, it is 2 PbO dot PbO2. There are plus 2 type 2 and plus 4 types 1. So plus 2, 2 PbO, 2 moles of PbO, 1 mole of lead 4 oxide, and 1 4 divided by 3 lead atoms. So you are getting an average of plus 8 by 3 in the X method. But when you are asked to really tell what are the oxidation numbers of the lead atoms, you will say plus 2 of 2 lead atoms and plus 4 for 1 lead atom. Similarly, this is the magnetic oxide. Ferrosulfuric oxide is FeO dot Fe2O3. By X method, you will be getting same plus 8 by 3. But 1 is ferrous plus 2 and 2 are ferric. 2 are ferric. So plus 2 plus 3 plus 3 by shared by 3 atoms. We are getting an average of plus 8 by 3, but which is meaningless. Yes, for monitoring equation, balancing purpose, you can write 8 by 3, no problem. But when you are asked to really say what is the oxidation number, so plus 8 by 3 is a paradox, is unacceptable. It is plus 2 and 2 times plus 3. Similarly, this is a very interesting molecule, tribromine octoxide. If you find by X method, it will be 3x minus 16 is equal to 0. So X is coming plus 16 by 3. But actually, if I draw you this structure, you will definitely Tell me what is the real status. This is the actual structure of Br308. Don't be scared at all, because I'm giving you the concept, nothing else, not explaining anything of chemical bond. Now, supposing you know the structure, then definitely the two are identical, then no charge development, no charge development. So this bromine will lose 5 electrons, 2 plus 2 plus 2. This is plus 5. Same is the case with this bromine. This is only plus 4, 2 on this side, 2 on this side. So plus 5 plus 4 plus 5 by 3, you are getting plus 16 by 3. Oh, I'm sorry. This 6, 2, 2, 2, 6. 2 plus 2 plus 2. It could have been 7 had there been heterolytic cleavage. This is homolytic cleavage because the two are identical. So it will be plus 6 plus 4, and this is also 2 plus 2 plus 2 plus 6. So 16 by 3. So the bottom line is, before we close, it is the bond structure which is to be known to find out what is the oxidation number of a particular atom. Yes, for simple molecules having one atom of an element other than oxygen, hydrogen, you can rely on the X method and carry on. But if it is a multiple atoms of a particular element, no, you have to know the bond structure. This is carbon suboxide. X method, you will have something different. C3O2. So this carbon is 0, this carbon is plus 2, this carbon is plus 2. So the average is coming plus 4 by 3. But actually there is nothing plus 4 by 3. It is plus 2 of 2 carbon atoms. They have plus 2 oxidation state, and the middle one is carrying 0 charge. This is called the tetrathionate ion. So if I draw the structure, you will find the actual oxidation number of each sulfur atom. Now see, these sulfur atoms are bonded with single bonds. This will have 0. And this will lose 5 electrons. So plus 5. This also lose 5 electrons. So this is plus 5, this is plus 5, this is 0, 0. So that we are getting 10 by 4 or 2.5. X method, you are getting 4x minus 12 is equal to minus 2. So x is getting 10 by 4, that is plus 2.5. Same is the case with is the case with thiosulfate. In thiosulfate ion, X method, you will get it is plus 2. But that will deceive you because it's a whole number. You will be deceived. Actually, if you draw the structure, again I am consoling you, don't bother about drawing. Try to understand the concept. So this is one sulfur-sulfur bond. So this will be 0 charge. And this sulfur will lose 4 electrons on these 3 sides. 2 here, 2 here. So it will be plus 4 and 0. So the average is coming as plus 2. But actually there is no sulfur having plus 2 state. The central sulfur is plus 4. The peripheral sulfur is 0. Is it not interesting? Now I will tell you the case where you will be finding a great interest. Now this is what we call Marshall's acids or peroxydisulfuric acid. Now if by X method you find, you will get plus 7 is minus 16 minus 14 plus 14 by 2. But if you are at all, you remember that sulfur belongs to group 6A or 16, it has 6 valence electrons. So how can it share 7 electrons? So it is improbable, impossible. So something is fishy about it. So once you know the structure, you can know that there is a peroxy linkage in the middle, there is a peroxy linkage, and this peroxy -1, and here this will lose plus 6, this is plus 6. So both the sulfur atoms are identical and plus 6. Because we were taking these two oxygen as normal, oxygen having -2, therefore the fallacy, the wrong calculation is due to the assumption that all the 8 oxygen atoms are of identical type. No, out of the 8, there are 6 of the normal and the other 2 are of the peroxy type. So that if you know this, then plus 2 plus 2x minus 12, and for the whole O2 it is -2. So you will get x is equal to plus 6. So the trick is, if you find certain oxidation number is exceeding the group number, according to the old nomenclature, you just drag it down to the group number. If it is plus 7, make it plus 6. If you are ignorant about bond structure. Now here this is peroxy monosulfuric acid or Carrot's acid. Here you will find plus 8, yes, plus 8. So drag it back to plus 6. It can't be, because there is a peroxy linkage. So sulfur is losing only 6 electrons. So because 2 electrons out of the 5 were of the different type, -1 type, that is why this wrong result is coming. N2O, this is the lapping gas. If we go for X method, you will be getting 2x minus 2 is equal to 0. So x is equal to plus 1. And actually there is now no oxygen having plus 1. If you draw the structure of N2O, later you know that. So here is a dative bond, a coordinate bond, where there is a plus charge here and a minus charge here. There are 3 lone pairs, forget about the lone pairs. And if you break down this, the 2 are identical, this will be 0 and this will be plus 2, because it is already a plus 1 and this will be losing 1 more electron and it will be having plus 2 and this is 0. So the average is coming plus 1. But actually the oxidation number is not plus 1. One of them is 0, the other one is plus 2. Right? If you do not know the charge concept, the formal charge concept, you can simply give a dative bond, a arrow mark sign to indicate a dative bond, then both the electrons will be lost by nitrogen because it was belonging to nitrogen. So it will lose 2 electrons because it's a dative bond. So it will be plus 2 and this will be 0. Similarly, in this case, I told you this is the climaxine. And we can call it chromium pentoxide, but it's not. If you see the actual structure of CrO5, you will be simply amazed. Simply you will be amazed that if you go by X method, you will find it is plus 10, which is unacceptable. Because chromium, if you do not know, belongs to group 6. Group 6 is in the transition metal group 6. So it has also maximum 6 electrons to share. So it can't exceed plus 6. How plus 10? So definitely some paradoxical case, some physics. So the actual structure, if you find, there are two peroxy linkages and one normal oxide. So these two minus 1, minus 1, minus 1, minus 1. This is minus 2. This is plus 6. And also it will be losing 6 electrons for double bond 2 and for these single bonds 4. So it will be plus 6. So this is not plus 10, it is plus 6. Now see how interesting it is. If you do not know the actual thing. For example, you are dealing with a very complex compound, not very complex, a complex compound. For example, you have you are asked to find out what is the oxidation number of cobalt. Now in this case, this is a complex ion having a metal ion, and these are called ligands. And there is a covalent bond between these metal ion and these ligands. Cyanide ion, which is an ion. So cyanide ion has minus 1 charge, and for 6, minus 6. And if it is X, so X minus 6 is equal to the net charge is minus 3. So X is equal to plus 3. So cobalt is in the plus 3 state. Now, let me tell you, this is bleaching powder. You will be very astonished that if it contains calcium ion, hypochlorite ion and chloride ion. In hypochlorite ion, if you go by X method, you will find plus 1. And this is a monoatomic radical minus 1. So this is plus 1 and this is minus 1. But if you are given this formula CaOCl2 by blending together, and you are asked to find the oxidation number of chlorine, you will get it is 0. So there is nothing called 0 here. One chlorine is in plus 1, this is hypochlorite ion, and this is chloride ion minus 1. And this, some of you might think it is plus 4, but experimentally it has been found that this is in the plus 2 state, and this is a polysulfide, S2 2 minus, just like S5 2 minus, S4 2 minus, these come under polysulfide. There is a sulfur linkage in between. So this is S2 2 minus, so Fe is in the plus 2 state. Rather, the average oxidation number of sulfur is minus 1, minus 1. I mean, in fact, both are minus 1, minus 1. Why average? Minus 1, minus 1. If there is one more sulfur, then it becomes an average. Otherwise, in this case, it is really minus 1, minus 1. But iron is in the plus 2 state, right? This is what we call the fool's gold or the iron pyrite. It looks like gold, but it is not gold. Iron pyrite. Now, to close the session today, we have 10, 15, 30 minutes, more than that. So even in organic compound, you can find oxidation number, which is of very, very less importance in organic reactions. So you can draw the structure, say acetic acid. If you are asked to find out the oxidation number of carbon, this carbon and this carbon, then carbon is more electronegative. It will gain 3 electrons because carbon is little more electronegative, and since this is carbon same, no loss, no gain, so this is minus 3. And what about this one? This will lose 3 electrons from 2 to 3 sides, and this is same, so this is plus 3. So this is plus 3, this is minus 3, and if you go by X method, by making 2x plus 4 minus 4 is equal to 0, you get X is equal to 0. But actually, this carbon is in the minus 3 state, this is in the plus 3 state. Similarly, you can find out for ethyl alcohol, there are 2 carbon atoms. You find out what is the oxidative state for this and what is for this. Now, to end off, I'll give you, now in a redox reaction, which will be doing the balancing techniques will be the next video, short video. It will be 30 minutes. I think we have exceeded 30 minutes. So this is zinc is here in the elementary state, uncombined state at 0. Now it is a +2 monoatomic radical. So there is an increase in oxidation number, which is called oxidation. And if there is a loss of electron or increase in oxidation number or oxidation, there must be some reduction. And here hydrogen is +1 and here it is 0, elementary state. And this decrease in oxidation number or gain of electron is called reduction. Similarly, in ammonia and chlorine, nitrogen is in -3, this is 0, this -3 to 0 is increase oxidation. So this is elementary state 0 to -1. So this is a reduction. Now see how interesting is this case. When you react with potassium dichromate with hydrogen peroxide, immediately you get this interesting compound, a very, very interesting compound, which you can trap it by using organic solvent. It's very unstable. If you lose it, if you leave it in aqueous solution in acidic medium for some time, it will decompose. So you have to put a trap, a net, organic solvent to extract CrO5, which we can call chromium pentoxide, but it is a chromium diperoxide oxide. Diperoxide oxide. Now see, this is, once you find there is no change in oxidation number, it is a non-redox reaction. It is +6 here. This is also +6. I told you how it is +6. So no change means no electron loss or electron gain, no change in oxidation number. This is -1 and here also there is -1. There are 4 oxygen of -1 type. So for such non-redox reactions, which we fondly call metathesis reactions sometimes, the balancing is done by simply heat and trial method. It's very simple. No, knowledge of pure electron loss and gain, how many electrons lost, how many electron gains. It's not required at all. Simply heat and trial. So you have 2 chromium here, so you multiply by 2. And there is 2 potassium, 1 sulfate, 1 sulfate. And 5 2s are 10, and out of the 10 oxygen atoms, 8 are of -1 type, because there are 4 oxygen of -1 type. So 8 of -1 type, so it must be 4 here. So that 4 2s are 8 of -1 type, 8 -1 type. And the remaining 2, which are of -2 type, will be here. So that, this will be it will be 4 2s are 8 plus 2, 10, so it will be 5. So that you'll find here 7 plus 4, 11 plus 8, 19 oxygen here, and this is 5 2s are 10 plus 4, 14 plus 5, 19. So that the logic I did here your 2 means there are 8 oxygen of -1 type. So there must be 4 H2O2. And then the remaining hydrogen 4 to the 8 plus 2, 10, that has to come from water, so 5. So this 5 oxygen also is taken care of. Here there is nothing, but here 7, out of which 5 are here and 2 are the normal oxygen are here, so that this is balanced. Now coming to this one, immediately if you just leave it for some time, you'll find this chromium so-called pentoxide will be giving oxygen. This is a redox reaction. This is a non-redox. For redox reaction, you have to have a trick to know which is oxidized. Next video I'll tell you some very interesting aspects of balancing redox reaction equations. Not that easy. You can't use heat and trial method every time. Now this first reaction is that, since there are 2 chromium, you have to make it 2 here. And immediately my reaction is there are a one molecule has 4 minus 1 type of oxygen. So there will be 8. So immediately I will make it, and then there are 3 sulfate, so I make it 3 here, so that sulfate ions are balanced. Now what I'll do here, so I will make 5 2s are 10 minus 2, 8, so I will make it 4, because this peroxide minus 1 has been oxidized to 0. And chromium is in the plus 6 state, we know how to find out, and this is plus 3. This is reduction. So that minus 1 type 8, that has given you 4 oxygen atom. So prima facie, we made it 4O2, right? But we can't balance, because we have 3 2s are 6 hydrogen. So we have to make it 3. Then oxygen cannot be balanced. Oxygen cannot be balanced because here we have only 2 normal type of oxygen, but we have 3 here. So here we have to reduce 1 oxygen atom. Here 10, here 11. 4 2s are 8 plus 3 11. So 1 oxygen atom from here has to be reduced. So what I did, 4 minus, since it is a molecule, so 1 oxygen atom means half oxygen molecule. So the coefficient I made it as 7 by 2. So I cut it, I made it 7 by 2 to equalize oxygen, so that I find, so this 7 by 2 into 2, 7 plus 3, 10, 10. That means out of the 8, only 7 has been oxidized. And the other one, peroxide, minus 1 type, has gone to minus 2. Do you find the interest? That out of the, 8 minus 1 type of oxygen, 7 have been oxidized to 0 state. 7 by 2 into 2 is 7. And 1 has been oxidized to minus 2. So not all 8 oxygen are oxidized, but 7 are oxidized. 1 is reduced. Of course, chromium is the main element which has been reduced, plus 6 to plus 3. But besides that, one of the oxygen atoms have been reduced from minus 1 to minus 2. Is it not interesting? And to eliminate the fraction, you multiply the whole equation by 2. So it becomes 4CrO5 plus 6H2SO4 gives you 2Cr2SO4 whole 3 plus 7O2. This 2 cancels, plus 6 water. Now we close this session, and I will definitely ask you for a vote. Give your feedback, and if you have not yet subscribed to my channel, do so, and like this video if you have really liked it. And for your practice, in the description box I have given a lot of references. You will get a lot of practice questions and its previous videos, like how to write correct formula, what is the solubility rules, how to know, build up the ionic equation. All this you can find out in the description box. You study of your own. Now I will be giving you some very interesting concepts, not in a very elaborate manner, but in a system, in a concentrated dose. Bye. See you soon in my next video.